Okay, welcome back. Now the demo that I'm going to do, I'm calling Young's modulus. I'm going to explain a little bit about this concept of Young's modulus, what it is, define it, explain it a little bit, and then do an actual demonstration, an experiment that we do in the class, and then to calculate the Young's modulus of different materials. Okay, so the definition of the Young's modulus of a substance is the force over the area. So this is called the tensile strain on the object. Resulting change in length divided by the original length is the tensile strain. Tensile strain. So you're dividing stress over strain. The units of the Young's modulus are going to be, this is a Newton per meter squared over meter. So the meter over meter, the units cancels. Newton over meter squared is pascals. So what is Young's modulus measuring? When you are taking a substance like this, like a book or something, and you are exerting a certain force on it, and the object is going to be basically experiencing a strain. So take any object like this, exert a force like this, right, to stretch it or to compress it, right? So you can take the same thing, try to stretch this, compress this, or to stretch it this way, like this. So then you're taking the force that you are exerting, right? And then you're dividing it by the cross-sectional area A. So you're saying F divided by A, the force that you are exerting over that surface divided by the cross-sectional gives you basically the pressure that you're exerting. Either the pressure to stretch it or the pressure to compress it. So the top is in units of pascals, pressure, that force distributed over that area. And then because you're exerting that force, the length of that object is increasing by a certain amount delta L, right? Or if you're contracting it, it's decreasing by delta L, right? So you're dividing the force over the area divided by the amount of increase of the length divided by its original length, L. So basically the proportion of the length of the object that actually expanded, right? So the ratio of how much it expanded to the original length. So the meters are canceling there, and this is the force that you're exerting over the area. So objects that have a strong Young's modulus can withstand a lot of stress, right, and still not stretch or compress a lot. But all objects will eventually stretch and compress or buckle under a certain weight, right? So here are the Young's modulus of different materials. The Young's modulus of plastic is going to be 1.79 gigapascals. So they're all pretty large in terms of pascals, pretty large numbers. Young's modulus of wood, depending on the kind of wood it is, and whether the wood is wet or it is dry, that all affects the results. It's going to be around 11.6 gigapascals, right? So what does that mean? Wood is roughly about 5 to 6 times harder to compress or stretch or to buckle than plastic is, right? And then Young's modulus of aluminum is 70 gigapascals. So aluminum is harder to stretch and compress than wood. Then you got here Young's modulus of steel, 200 gigapascals. So the steel is among these objects, it is the hardest to bend, to stretch, to compress, and to buckle, right? So that kind of makes sense because steel is a very hard substance. So it's going to take a lot of pressure before you can actually bend it or stretch it or compress it. So let's do this experiment here. I have a piece of wood. I'm going to put it over certain cylindrical rollers, these cylindrical rollers, right? I'm going to put a certain amount of weight at the middle until the wood starts to buckle like this, and then go down, and then until it reaches the table. It bends down and reaches the table. So the Young's modulus for that particular kind of situation is given by how much weight it took to make it bend. After it bends, it's going to look like this, right? It's going to look like this, and it's going to be hitting the table like that, right? So the Young's modulus, the more weight it took, of course, the more weight it took for it to bend, the bigger its Young's modulus is, right? The L is the distance between where it's touching the cylinders, right? So this is the L. Not necessarily the total length of the ruler, right? But it's the length between the contact points, between where it's touching the cylinders. So this is saying the Young's modulus depends on how much weight it took, the length of it cubed, divided by 4b. The b is the breadth of it, which means it's the dimension that's coming out of the board, right? Or into the board, like this, like this, like that. So that's the b. It's the dimension that you don't see. It's coming out of the board or into the board. So it depends on the linear power of the b. The d is the thickness of the ruler, right? So the thickness of the ruler, d. So for the thickness, it depends on the thickness cubed. So notice here, the L is cubed, the thickness d is cubed, the b is the breadth coming, it's perpendicular to the direction of the force that I'm applying, right? So the b only depends on the linear distance of the b, whereas the thickness depends on the cube. The y is the distance that it's going to go down and hit the table, right? So in this case, the y is just going to be the same as the diameter of the cylinder. So the y will basically be how much you're trying to bend it, right? How much you're trying to bend it up or down, like this. It's the bending amount, like this, from the plane of the ruler, like this and like this. The d is the thickness of it, the b is this amount, okay, the breadth of it, and then the L is the L. So let's do the experiment here. And that's going to be my y value. That's 1.59 centimeters. 1.59 centimeters. That's my y. Okay. My thickness d is going to be the thickness of the ruler. That's going to be 8 millimeters, so 0.8 centimeters. 0.8 centimeters. Okay? And then my breadth, B, is going to be the width of it, like this. That's going to be 2.55 centimeters. Okay, while I'm at it, I'm also going to be doing the Young's modulus of the plastic ruler. That's going to be 2.99. 2.98. So the B of the plastic . Okay, so now let us put the cylinder. I'm going to put the cylinder at the 90 centimeter mark, and the other one at the 10 centimeter mark, 90 and 10. So the effective distance is the length between the 90 and the 10, that's 80 centimeters. So that's my L value, 80 centimeters. 80 centimeters, right? So then I'm going to measure how much weight it takes to bend this all the way and touch the table. Keep putting weights on it. Touch the table. I don't want to touch it too hard. I want to be able to kind of barely make a piece of paper go through it. Okay, that means I'm not touching the table too hard. Okay, so that's about right. Maybe a little bit more. Okay, that's about right. Okay. Now let's do the plastic ruler while we're at it. I can put the cylinders around the 2 centimeter mark and the 28 centimeter mark. Okay, so the distance between them is going to be 26 centimeters. So the 2 centimeter mark and the 28 centimeter mark. So the L is 26 centimeters. Okay, so then put some weights there. This one is going to bend easier. Okay, so that's about it, right around there. So it took how many grams here? Okay, so for the plastic, it didn't take a lot of grams. That's 50, 100, that's 200 grams, 210, 220 grams. So the mass that it took, 220 grams. So the result that we got was similar to the result that we expect. It's in the ballpark, 11.6, 14.6. Even though there's about a 3 gigapascal difference, that's about an error of maybe 20-25%. But that is still okay because we don't exactly know the kind of wood that we have, and it also depends on the condition of the wood. So that could affect all kinds of results, but I am glad about the result we have. Now, in an experiment that we do in class, we do both sides because some rulers more easily bend in one direction than the other, and we take the average of the two. So if I had done that, that might have even improved the result also. Okay, now let's do the plastic one. For the plastic, how much weight did it take? It took 200 gigapascals. Okay, for that one we expected to 1.79 gigapascal. That one we're even closer, right? So we're down in the 1 or 2 gigapascal range, whereas for the wood we're up in the 10 to 15 gigapascal range. So definitely wood is harder to compress or stretch, right, and to bend, and the plastic is a lot easier to compress, stretch, and bend, right? So 2.2 gigapascals is a very good result. One of the other things we could do with this demo is change the length of it, change the length or change the Y, changes some factor one at a time and see if this cubic nature or if the linear nature is correct, okay? So for example, let's say I want to just change the length L and see how much weight am I going to take? How much weight is it going to take to stretch that, right? So let's say instead of 80 centimeters, I had used 60 centimeters. I brought in the cylinders closer. How much more weight am I going to require, right? So instead of asking what is the Young's modulus of the ruler, I'm asking what's the nature of the Young's modulus? How does it depend on the effective length of the object? So then I can say, I'm not changing the Young's modulus, I'm keeping this constant. All I'm changing is the length. So that means W1 L1 cubed is W2 L2 cubed. So all I'm doing is changing the length. So if it took 2.41 kilograms, 2.41 kilograms when the length was 80 centimeters, right? How much weight is it going to take if it was 60 centimeters, right? So W2 60 centimeters. So it's going to take a ratio of, now this is the theoretical, okay? What if I change another factor, okay? What if I just change the width of the cylinder that I placed them on, right? So I'm going to use now these cylinders which are thinner. I'm going to measure their diameter. It's going to be 1.27 centimeters, okay? So instead of the Y being 1.59 centimeters, it's going to be 1.27 cubed, right? So then, if I want to calculate W2, I'm going to say Y2 over Y1, W1. Notice we're not going to cube that. So then Y2 is 1.27, Y1 is 1.59, W1 is equal to the 2.41 kilograms, right? 2.41 kilogram. So then W2 theoretical, we expect it to be what? Okay, so we're going to go back to the ruler, put the cylinders at the 85 and 25 centimeter mark, 85 and 25 centimeter. So the difference between 85 and 25, that's going to be 60 centimeters, right? 60 centimeters. So my effective L is 60 now. Now how much weight is it going to take? The bottom is touching it, and I can actually slide a piece of paper right underneath, barely. You see? So therefore, this proves that it's about 5.5 kilograms. So let's count that. Half, 1, 2, 5, 5.5 kilograms. So my experimental answer was 5.5 kilograms. Okay? W experimental, 5.50 kilogram. Okay, now let's go back to when they were at the 90 and 10 centimeter mark, right? The length was 80 centimeters, but instead of using those cylinders, I'm going to put these cylinders. I'm going to change the Y value, right? So now how much force should it take? So go back to the 80 centimeters. Okay, so then I'm going to have here half a kilogram, 1 kilogram. Okay. Okay, and this is 1,900 grams. Let's see if I can slide the paper. So that's 1,900 grams. Now if I can put a little bit more maybe. This is 10 grams. Okay, and then a little bit more. Okay, barely. So about 1,920. Okay, so I'm getting about an answer, 1,920 grams. W experimental, 1,920 grams. Okay. Okay, so from this you can see that the ratio concept work. We were able to show that when the length went from 80 centimeters to 60 centimeters, the weight that it took to make it bend went up quite a bit, a lot bigger. So the cubic nature is proven, where the theoretical result was 5.7 kilograms, and then I put 5.5 kilograms and I went down to the amount. So the original amount was 2.4 kilograms, but it increased by a lot of fold all the way up to 5.5 kilograms, right? So the cubic nature of the L dependence matters. So what that means is that if you take something and you hold it at a certain distance, it takes a certain amount of force to bend it. If you decrease the distance a bit, it takes a lot more force to bend it by the same amount. So proportional to the cube of the distance of where you're holding it. So if you hold it here and you try to bend it, a lot tougher, right? Now, the dependence on how much you're trying to bend, the Y is the distance that you're bending, that one depends on linear. So if I bend it a certain amount, right, and then if I want to bend it twice that, it takes twice the amount of force. So a certain amount, and then twice that amount, twice the force. You don't cube it. So you don't have to say 2 to the power of 3 is 8, right? So then that one also worked. We showed that the W2 theoretical was 1.92. So instead of 2.41, it predicted that it would only require 1.92 kilograms. And the result that we got was actually 1,920 grams, which is also the same as 1.92. So you can see here how you can do a good experiment to understand tensile stress, tensile strain, Young's modulus, show what the Young's modulus of different materials is, and also do an experiment to test the dependence of the force that it takes to bend something based on changing a certain factor at a time, like the L and the Y. Okay? Thank you very much.